Well, for your information, we haven't started grading yet. No, we'll do it this week. What? No. I had other things to do. Okay, today we are going to cover log-log analysis, and this will be the basis of the well-test analysis, and this will be what you will do in the next classes. And in the next exam, in the next quizzes, in the next exercise problems, you will always start with the log-log analysis. Okay? So it's like, I mean, how many of you wanted to become doctors in your life? None? Have you ever wanted to become a doctor? Why? I'm a doctor, MD. It's a cool thing, right? So nobody wants to become a doctor? Okay. Okay, so nobody wanted to become doctors? No. But anyway. Okay, that's good. Okay, from now on, we all become doctors, but we will become well-testing doctors, okay? And what we will do, we will diagnose, and then we will go to analysis. So what we... Bless you. So we will always start with the log-log plot, and the reason is for the flow regime identification. So this is a problem we worked on before the exam. And our primary tool will be the well-testing derivative. And it will be the most important thing. So it will always tell you whatever is going on with your production. Okay? So, is there a ruler? So, looking at the well-testing derivative, if you see a unit slope, what does it tell you? Okay. So the first thing I'm going to do, I'm going to identify the flow regimes. And when I see the unit slope, and it means the wellbore storage domination. So I'll just throw my pole here. And this part is wellbore storage domination. And what is the equation for wellbore storage domination? You don't remember? Okay, so and here we are looking at four possibly flow regimes, and we already identified the first one, which is the wellbore storage domination. And then the next thing we are going to do is to find the horizontal line, which gives us the infinite acting radial flow. But in this case, it's hard to identify, because the reason is, you see, the derivative is kind of bending down. So in a pressure build-up test, when you see something like this, in the well testing derivative, this tells you that you are under the boundary dominated flow regime. So here you are seeing the boundaries. So I am going to draw my second pole here. And I'm going to say boundary effects. And when you see the boundary effects, what you can get from the boundary effects, what you can estimate actually. You already saw this in the exam. I mean, okay, P average. And this part is called the well-bore storage distortion flow regime. And in this part, basically, you can't do anything. There is no analysis here. And the reason is you are producing both from the well-bore and you are producing from the reservoir. And here is the other part we are interested in, and this is called the infinite acting radial flow. What?
It's at the average pressure through that area.
No, it's not the average reservoir pressure, it's the constant. It's the horizontal line. It's the pressure value read. Here. Yeah, 30. But you don't have to find 30 exactly. I mean, you can find 35, 25, something like that.
You just pick a midpoint in there?
What?
Did you just pick like a midpoint?
Yeah, because the reason here, the boundary effects are distorting your horizontal line. But you need to find the horizontal line to proceed to analysis. Okay, and what was the equation for the radium flow regime? Okay. Okay, so it's the constant plus the MSL times log delta T, right? This was our equation for the radial flow. Okay, so if we take the derivative, which is and derivative is so basically your MSL, the slope of your straight line, will be just the value you read from the plot times 2.303. Okay? Okay, this was the first thing we found. We found the horizontal line which gives us the radial flow regime. Yes?
When did you get the standard rate?
Oh, it's the conversion from the log base 10 to log base natural logarithm actually. And the second thing is to find the Van storage. So how do we do that? Okay, what we do is, since the flow regime is power law, which is okay, this is the equation for this straight line. Y is equal to A times X raised to power B. So if you make this one, then you get A, right? And here, actually, our equation is delta P is equal to M Albor storage times delta T so when you come to here, so what I did was I find the time where delta T is equal to 1, and then I read the value from the model, which is our line, and gives us the 800 psi per hours. So this is our M Valbor storage. And from now on, in all of the things you will do, you have to show this. You have to show the work I did. You have to show the flow regimes, you have to show the poles here, and you have to identify the flow regimes and write down what is wellbore storage domination, where is boundary effects, and where is the radial flow. And then you need to show where your radial flow regime is and where your wellbore storage is. And then you proceed to find the values for the wellbore storage coefficient, permeability skim factor, and average reservoir pressure if applicable.
PSI per hour?
Yeah, PSI per hour.
It is PSI per hour.
Mm-hmm. Okay, any questions about this one? So this will be our basis, and then when we go to the semi-log plots, we are going to use this MSL that we found from the log-log plot. Okay, so what is our MSL? It is 2.303 times 30. So which is like 70. So it will be like 70 psi per cycles. And then in the early time Cartesian plot, the slope we are going to use is this 800 psi per hour. Okay, did you write this down? Yeah.
Does the subscript RF stand for radial flow?
Yeah, RF means radial flow. And the dish means the derivative. Yeah.
Can you get the average pressure from
The Muscat plot. The Muscat plot, you remember? Okay, so this is basically the key that I did last year. Okay, so let's find the values. The values will be so the wellbore storage coefficient is equal to QB over 24 times the wellbore storage. Actually, I have found 970 psi per hour before, so I'm going to use that. And that gives me 0.0122 barrels per psi. And the equation for the permeability from the log-log analysis is this: 70.6 QB mu over H times 1 over delta P dash RF. So how do you relate this to the semi-log permeability? and is MSL is basically the natural logarithm 10 times the delta P dash RF. So which is 70 psi per cycle. Okay, so that gives me a permeability value around 77.65. And then now, once I find these values, now I am going to proceed to the other plots. And then I'll start with the Cartesian plots, and I'll make sure that I'm going to use this slope in that. Okay, so and you remember our value for the N-Labor storage is 970 psi per hour. So I am going to force this slope on this plot. So how am I going to do this? Okay, so tell me how am I going to force the slope? So I know the slope, which is 970 psi. And if I take x1 is 0 and x2 is 0.4, I can find delta y, right? And what is the value for delta y? Is it right? So if I start from 600, then my y2 should be around here. Okay, so I have 2 points, and the straight line will be, I'm going to connect these 2 points. Okay, and this is your straight line. And then what you are going to do, you are going to shift this straight line . Yep.
Why not simply start at 700 with that aggregation?
But you can't do that, because if you do that, then you have to find the value for the slope. Or you can do that also, I mean, but you will be out on the plot, I guess, on the axis. But, I mean, whatever you do, make sure that your slope will be the same from the log-log plot.
Yeah.
Okay, that's the point. I mean, I believe this is easier, but if you think this is not very easy, then you can do your own. But, I mean, make sure that your slope should be 970. So the slope of this straight line is (970 psi per hour). So once I construct this straight line, I shifted it onto the data, and then here is my Weber storage model, okay? And this value will be the pressure at the instant of shut-in. Okay, and then the next thing you are going to do, you are going to put your pole here. So once the data deviate from the straight line, it means that you are not in the Valbor storage domination regime anymore. And then here, so this is the Valbor storage domination part, and this is the Valbor storage distortion part.
How do you use dead cell blocks?
I choose it.
No, you got 388. How do you use it on the plug?
No, what I did was I take the Y1 as 600, so delta Y is 388, right? So I just add 388 and find the value for Y2. Okay, 600 is our Y1.
Okay.
And Y2 will be 600 plus 388.
Okay.
So, which is
It's not
900.
700, it's like 900.
No, I mean, the first thing I did was I constructed the straight line and then I shifted up. Okay? We'll discuss later. Okay, any questions about this? So what I did was, summarizing it, I found the Valbor storage slope from the log-log plot, and then I used that slope value on this, and I am forcing it. That's the idea. Okay? So in other words, I am making sure that the value for the slope is correct. Okay? Because the reason is you already found the Valbor storage coefficient value, which was 0.0122. And if you don't do this, don't do the procedure I did, and find the Valbor storage coefficient like 0.1 using your own slope value, this means that your analysis is not consistent. Okay, you cannot find two values for the Valbor storage coefficient. I mean, you can find a very close value like 0.015, something like this, but it cannot be 0.1 and 0.0122. So the whole idea is to make your analysis as consistent as possible. Okay, the other thing, now we are on the semi-log plot, and you remember our MSL is (70 psi per cycle). Okay, so I am going to do the same. So I am taking the 400 as my first point, and 1, 2, 3, 4, 5. And Y2 will be 70 times 5, which is 350. Okay, so I found 2 points and then I'm going to connect them with the straight line. Okay, so now I am going to shift this straight line onto the data. Okay, and we already find our straight line. So now we will identify the flow regimes. So since we are using the same slope value, our permeability value will be the same, right? So it should be 7.65. But one thing I cannot find from the log-log plot is the skin factor. So I need to find where PWS is equal to 1 hour, which will be here. Okay, so once I find the PWS 1 hour, and then I can find my skin factor. Okay, and that should be it. So in the end, all of your analysis will give you the same results. And you start from the log-log plot, and the values you find, you force the slope values on the semi-log plot and the Cartesian plot, and find your permeability, skin factor, valve storage coefficient, or whatever you need. And the last one is the Hornet plot, and you will do the same, but the only thing which is different is your axis. So make sure you be careful about the axis, but other than that, everything will be the same. MSL will equal to 70 psi per cycle. So make sure your straight line gives the slope value which is equal to 70. Okay? I mean, it's easier to identify the flow regimes on the log-log plot with the derivative, so you are using that, because when you look at this plot, I mean, can you see clearly where the straight line is? But you can start from this, but I mean, you have to find the same value on the log-log plot. So it cannot be different. I mean, the permeability you find from here is 10, let's say, but it cannot be 5 on the log-log plot. So make sure they are consistent and very close. Okay, any questions about this thing? What? No. You don't need to. I mean, I give you the equations. Okay, let's do the quiz now. Oh, by the way, yeah. Yeah, you can do that on the test, and you say, I am shifting the line. Yeah. But you must show the line on the data. Show the line on the data. You must do that. Yeah, sure. Also, you have an exercise problem due on Wednesday, and this is based on the quiz you are having today.